Might have to say rocket. Good. Recording.
No, it'll come back.
All right. I'll be the chairperson. We start. Steve. Thanks for coming. It's such a tough job to do the last talk at a meeting like this, but if you can prove that Steve has already been a success, look how many people are in the audience. It's just great. So thank you. Steve can talk to us about Kekule spirals in twisted bilayer graphene.
Thank you. It's a pleasure to be closing up the conference. It looked like it was a great conference. I'm sorry that today was the only day that I was able to make it here. So I'll be talking about twisted bilayer graphene. As you heard from Pablo today and yesterday, it's an incredibly rich system with a lot of complicated phenomenology. I feel like I'm actually kind of a newcomer to the field. There are a lot of people who spent much more time than me really digging into all the details, and there are a lot of complicated details of the system and a lot of complicated questions. I was going to say that if you ask me questions, it may be that a lot of the answers are I don't know. And I was hoping I could defer to Pablo, who unfortunately had to leave this morning. And in absence of Pablo, I was going to defer to Ashvin, who also apparently had to leave. So we're just stuck with the answer that I don't know before you even ask the question. But actually, much of the beginning of the talk, about the first half of the talk, is really talking about work in Ashvin's group, because I think he laid out, and his group and Andre Bernovik's group and Alan McDonald's group really laid out a good structure of how to think about the twisted bilayer graphene system, which I'll try to explain to you first before I try to explain to you what Kekule spirals are. Is the microphone going on and off and being really annoying?
Yeah.
Should I just take this off?
No.
If you can.
Move it up.
Yes.
But not too far.
Yeah. All right. So this project is with well, the main group is up on the top row. Yves Kwan and Gwen Ragnar, both postdocs now. They were both graduate students at Oxford with me and Sid. And Nick Boltink, who was a postdoc at Oxford with us. He was also a postdoc previously working with Ashvin and Mike Zalatel. And the person, I mean, those are the three people who really did the heavy lifting of this project. They're all fabulous. Nick now has a professorship at Ghent. But the person I really want to thank a lot for this project is Sid, who's the moral leader. And he kept dragging me into the subject as much as I didn't want to be. I saw all this exciting stuff going on in twisted bilayer graphene, but I also saw, these really big, powerful armies, Andre Bernovik's group and Ashvin's group and Alan McDonald's group. And it looked like they were running so fast. And I kept thinking, how can I possibly compete? Yes. Take off.
Move it down.
Down here.
Yes.
Yeah. Okay.
Try that.
Okay. Thank you. So I kept thinking, how can I can possibly compete and come up with anything that these guys don't have, because they're publishing, these 80-page papers every week. No joke. But Sid said, no, it's a really interesting field. There's lots of stuff left for us to do. Let's do it. And he convinced me and the other guys to really start digging into this. In other parts of the project, we collaborated with the Berkeley group, Mike Zalatel and Phil here at Sujima. I'll talk about that work a little bit. Also, Erisberg, who is also here this morning and now left. Yichen, who was stuck with us earlier, and Malcolm, who's sitting right over there for part of his master's project. Much of the interesting stuff I'm going to talk to you is summarized in this PRX from 2021. Some pieces of it are spread out on a number of other publications. Actually, this lower paper down there, Wagner et al., won some best theoretical paper of the year award, which Glenn is currently picking up in China this weekend, which we're very happy to have such awards. I never even knew it existed. But actually, if you really want to learn about the subject, I would recommend reading the PRX, not the PRL. So probably a better paper. Okay, anyway, so let me summarize up front because I know people never get to the end of their talk. This is our picture of a Kekule spiral. So this is twisted bilayer graphene. This is the big red blobs are the Moiré superlattice. So you slightly twisted two graphene layers and put them on top of each other. And these are the so-called AA regions, periodic in the system. And then down here is a zoom in on one graphene layer. And I've drawn some of these bonds in red, thicker in red. And this, if you imagine these thicker red bonds being a little bit shorter, that's known as a Kekule distortion. It's a tripling of the unit cell. Now, there's more than one way to make a tripling of the unit cell. I could have, for example, chosen the other bonds to make shorter. And there's actually lots of ways to make a Kekule distortion, a tripling of the unit cell. And if we think of that different ways of making distortion as a vector, which lies in the plane, that vector rotates from place to place. So if you might not be able to see it, but there's vectors drawn here, and the vector points down here and over here and up here, and that rotates as you go through the system. So that's the structure that we are proposing. And I'll make it clear. Actually, I'll show you experimentally exactly what it is in a moment, and I'll explain why it happens as well. And generally the wave vector associated with that twisting is incommensurate with both the underlying lattice and the Moiré lattice. Okay, so that's the structure that we're going to argue is there in a lot of the experiments, and it's real. This beautiful experiment by Ali Yazdani's group, which he's plotted it slightly differently, but as you go from this region to this region to this region to this region, you've drawn a vector which rotates incommensurately with respect to the underlying lattice. And I'll explain exactly the experiment. If we get there, I'll explain the experiment, how they did it, and what it is they conclude. And I should also say that the lead author on this paper, if you're interested in learning about the experiment, which is a brilliant experiment, Kevin Knuckles is the lead author, and he has a very, very beautiful talk online on his Princeton website, which is recorded. And I learned a lot from listening to his talk, because I thought I understood the experiment. Then you think about it harder and you think, well, actually, I don't understand it at all. And then you listen to the talk and you go, oh, now I understand it. So it's really very well given. Okay, so all talks of this sort start with this picture, a Moiré pattern, any periodic picture, and you rotate it slightly and put two copies on top of each other. You see a longer wavelength modulation. Probably the most important, maybe Pablo told you this already, but the most important thing I'm going to tell you today is that Moiré should not be capitalized. Did he tell you that? He told you that, or he didn't tell you that? Okay, this is the most important thing I can tell you. Moiré is not someone's name. It comes from the French fabric processor Moiré, which is a textile process where you do exactly this. You put down two textiles on top of each other at small angles, and that came from the word mohair, which is the wool made from the Angora goat, not to be confused with the Angora rabbit, and that which is what we usually think of when we talk about Angora, and mohair, that word comes from an Arabic word mukayyar, and I'm told, which means the best or the chosen, because that kind of goat is the best goat for making wool. And does anyone speak Hindi?
Yeah.
Yeah, I'm told that the word mukayyar exists in that as like the boss or the chief or something like that. Is that correct?
Yeah, maybe.
Yeah, that it's made it into that language as well. So, okay, that's correct. Anyway, so the best. So anyway, the Moiré physics is the best or the chosen physics. Okay. So if you rotate, so that I'm sure Pablo told me this yesterday, so I won't belabor it. But when you take two graphene sheets and you rotate them with respect to each other slightly at a small angle theta, you get a periodic superlattice, and the length scale of the superlattice is the underlying lattice scale divided by the angle theta. So if theta is very small, you get a very long length scale. When the real space expands, reciprocal space shrinks, and a way to see what happens to reciprocal space is you have these. Graphene itself has a hexagonal boron zone. And so you have two hexagonal bronze zones, which are slightly rotated with respect to each other. And if you sort of connect up these 2 points, that makes boundaries of the Moiré or mini bronze zone. And these are the important bronze zone for our problem. There'll be one bronze zone here around the K points, and then another bronze zone opposite at the K prime points. And actually this corner is the same as this corner is the same as this corner, and so on. Okay, so we're working within the mini bronze zone or Moiré bronze zone all the time now. So the field really started with the work of Mr. and McDonald in 2011, where they pointed out that when you go from the big bronze zone to the mini bronze zone, you fold over the dispersion many, many times. And so all sorts of things start overlapping with each other. So here you can see, here's a spectrum as a function of K. You see these Dirac points from the original graphene, but as you get up into the spectrum, everything gets folded over into itself and really, really complicated. Oh, Ashwin is here, fantastic, because I did, you missed my comment that it said that I don't know anything, and any questions will go to Ashwin. What they noticed is that under certain conditions, the repulsion or the anti-crossing of these bands will switch everything down to a very, very flat band. And the flat band that we're going to be working with, this is the blow up of what's going on there, is really 8 central bands. So there's a bunch of degeneracies there. There's a spin degeneracy, a valley degeneracy, one additional degeneracy that you can think of roughly a sublattice degeneracy, all stuck in here, and it's fairly flat. An important thing to keep track of is the filling of these bands, and conventionally you label filling from charge neutrality or the middle half-filled bands. If everything's filled up exactly halfway, we call that filling 0. And if this entire central band is empty, that's filling -4. And if the entire central band is filled, that's filling +4. Okay, it's kind of a good exercise to sort of play with these dispersions. I tried to actually get ChatGPT to write code to do this diagonalization for me, and it did not actually manage to do that. But Sid tells me that it's because I didn't correct it. That if it does the wrong thing, you have to say no, you did this incorrectly. Please fix it. And if you say that enough times, it actually gets it right. So I haven't tried that. So anyway, if there's no coupling between the 2 layers, you see there's nice Dirac point and some touchings here. But as you add coupling between the layers, you start to see a bunch of anti-crossings, like there's an anti-crossing opening up here, an anti-crossing opening up here, and you increase the coupling between the layers, and this central band starts squishing down, and eventually when you turn the coupling up to full at the magic angle, you get a very, very flat band in the middle. Okay. So this is the picture that started everything off, Pablo's work. This is how it was labeled in the original paper, that as a function of electron density and temperature, you have these superconducting domes. There are metallic regions and there are insulating regions, which they labeled as Mott insulators at the time. And they said this looks a lot like high TC superconductivity, where again is a function of electron concentration and temperature. You have Mott insulating regions and superconducting regions. So this looks very, very similar. And the rough picture, here's your Moiré graphene. And the picture they had in their mind is that you can think of these what they call AA regions, the regions where the 2 lattices lie right on top of each other, as being sites. And then you have some sort of Hubbard model with electrons hopping from site to site. Now, I think we now understand that twisted bilayer graphene is somewhat more complicated than just a Hubbard model, or maybe simpler than a Hubbard model. It's different from a Hubbard model at any rate. But there were some things that they said were certainly right. And the things that they said that were certainly right is that these insulating regimes are coming from correlation physics. Not exactly the same as a high TC, but certainly correlation physics. And interrupt me if there are any questions, and I can have. Okay, good. And I'll have Ashwin answer and all the questions. Okay. Anyway, this is actually this is data from a different group, but this is just to show different sample, that all the integer fillings have obvious correlation physics occurring at filling 3, 2, 1, 0, -1, -2. This the resistance is here, and then the temperature pictures are down here. And when nu equals 4, that means all central bands are filled. You just have a band insulator. Nu equals -4, all central bands are empty. You just have a band insulator. But all the things that look insulator-ish, some are real insulators, like -2 in this picture, really good insulating. This one just looks like it's some sort of anomaly. It's not quite an insulator, but all of that is coming from correlation physics. Okay. So a good place to, as I said, Ashwin missed this also, that about half my talk is going to be talking about his work. But a really nice, yes.
Are you going to tell us in what way it's not insulator?
I'm probably not going to tell you that, but everything that I'm going to say really starts from the band limit. So I'm not going to think, I'm really starting with everything from bands, and the bands do have form factors where certain bands have sort of lobes that live near those central points, but really we're thinking about everything starting from the band limit. Slater. So everything is Slater. Everything is Slater. Matter of fact, the most sophisticated technique we're going to use is Hartree-Fock. So it's very.
And then you tell us how you get a gap in that scenario. Then you
filling. I will tell you that.
Oh.
Yes. Yeah. So there's this really nice work by Ashwin's group, which gives you a really good starting point. I think it's the right starting point. It's a very good starting point, and I should say that Andrew Dernovic's group has a slightly different approach to a very similar starting point, but the idea is to start with an exactly flat band. And there's several ways to get an exactly flat band. One is known as taking the so-called chiral limit, and there's a parameter in the underlying hopping model, which is basically known as the chiral ratio. It's the hopping between layers in the AA regions versus the hopping in the AB regions, which are slightly different from each other. Experimentally, it's thought to be the ratio of about 0.8. But if you tune that down to 0, then you get, under certain conditions, you get an exactly flat band. And this exactly flat band is made up of 8 completely flat bands, of which 4 of those bands have Chern number +1, and 4 of those bands have Chern number -1, so they look like Landau levels, and that's a really nice starting point. Now, for those of you who may not be familiar with it, this is Chern over here. SS Chern. He's known as the father of modern differential geometry. Apparently, he was so famous in China that he more or less couldn't leave his house because the paparazzi would follow him. No joke. And so he spent a lot of time in the United States where he felt he could concentrate on doing mathematics. He was extremely famous. Well, he was extremely famous everywhere, but paparazzi don't follow mathematicians in the United States. But anyway, so Chern would probably be entertained to the way we've used his name in terms of in this context. But we would have to first explain to him that an insulator is actually a fiber bundle. Then he might say, "Oh, okay, now I understand." But the theorem, the important theorem, which really goes back to Thales and Laughlin, is that any two-dimensional insulator always has a quantized Hall conductivity. So GXY, sorry, this should say conductance, not conductivity. The quantized Hall conductance, GXY is some constant C times E²/H, where C is known as the Chern number. If you're thinking about non-interacting electrons, where you just fill in some integer number of bands, and then you have a gap, and you have empty bands above it, C is just an integer. It's quantized Hall effect. Okay, this is what the Chern number is, the coefficient of the quantized Hall effect. It's of course possible for some particular system that C is 0, in which case you have the kind of bands that you learn about in Ashcroft and Merman. But it's also possible that C is +1, and that's like a Landau level. Okay, so this limit where you start with a completely flat band is sometimes known as the chiral limit, or the strong coupling limit. And it's called strong coupling because you've completely killed the kinetic energy, and then everything is just interaction after that. Okay. So in this limit, you can label your 8 central bands in terms of 3 quantum numbers: sublattice, valley, and spin. And the Chern number of the band is the product of the valley and the sublattice. So this limit, which I was really developed by Oshman's group, along with Nick Boltnick and Heslam Khalef and a bunch of other people, and then also Andre Bernovik's group, is really interesting because what you have is you have an enormous symmetry. You have 4 bands with Chern number +1 and 4 bands with Chern number -1. And it's completely symmetric under rotating between any of those 4 Chern number +1 bands and Chern number -1 bands. So we know a lot about, and each of these bands you can think of as being like a Landau level, electrons in a magnetic field. Now we have a lot of experience over the last 30 years about what happens when you have multiple Landau levels, like a spin up Landau level and a spin down Landau level. And if they're very close to generating energy, we know what happens. What happens is that the electrons choose one direction, and then you just fill a full Landau level of the electrons pointing in that direction, become ferromagnetic. So you choose some basis and you fill up an entire Landau level in that basis. That's known as flavor ferromagnetism. Okay, does that make sense? So good. Yes, good. All right. So that's the basic intuition behind this starting point. So then you can add the interactions as an afterthought to decide which of these flavor ferromagnetic states are most favored. So whenever you have some number of the central bands filled, and remember we start counting from nu equals -4. So when nu equals -4, you have 0 bands, and when nu equals 0, you have 4 bands. So you have some number of bands out of the 8 of the central bands are filled. And the idea is you're just going to fill some number of those central bands in a Slater determinant, and that's it. That's going to be the ground state. But before you fill bands, you can start making superpositions. So for example, if this was just spin up and spin down, you can make some superpositions, spin up and spin down to say put the spin in a plane and then fill an entire Landau level of the spins pointing in the plane. And in this case, it's a little bit more complicated because we're choosing the valley K sublattice A spin up and the valley K prime sublattice B spin down and superposing them with some phase to tilt the pseudospin in some complicated direction before we fill the band. Okay. So far, so good? Yeah. Okay. Anytime you superpose the K and K valleys, you are going to introduce a wave vector between the 2 valleys. That's K minus K prime. That's going to end up with a tripling of the graphene unit cell. Okay. So when you do this, you then add various perturbations to try to decide which of these flavor ferromagnets are most favorable. And one ends up with a picture that looks kind of like this. This is the possible filling fraction, and each integer I've labeled a name for a particular state that's predicted by the strong coupling picture. And they have abbreviations. So QAH is quantum anomalous Hall. That means it's a quantized Hall state. It has a non-zero net Chern number. And whenever, if you're just filling up Chern number +1 and Chern number -1 bands, whenever you have an odd number of bands filled, you're going to have a Chern number of either +1 or -1. If you have +1s and -1s, you always have one left over. So any of the odd states will have a non-zero Chern number. Some of these are labeled with IBC. That means intervalley coherent. That means there's some sort of tripling of the unit cell or coherence superposition, like this one, between K and K prime. And so you have the triple unit cell. And then there's this thing that seems rather ubiquitous in this approach called KIBC. And this is it's an IBC state, an intervalley coherent state, with a Kramer symmetry, which is not the actual time reversal, but sort of a modified time reversal. This Kramer symmetry, I don't want to go into too much detail of what it is, but it has an interesting property that you have a tripling of the unit cell, but no density distortion. The density is flat, but you have currents running around in sort of a 3-unit cell pattern. Yeah.
I have a question concerning all of these different ground states, which then are sort of the degeneracy is lifted by some perturbations.
Yeah. So you put in whatever perturbations you choose, various interactions and interactions with substrate and so forth. And then given those interactions, you decide which ferromagnet is most favorable.
So can one see these other nearly ground states experimentally, excitation into this other?
So you would think that if you would think that I might be able to rotate this up to some excited. I don't know how you would do that, but presumably it's some excited state, the many body excited state that's up there. I mean, there you might imagine there's some of them will have local, some local Goldstone mode.
Yeah, I'm thinking of
Some of them will, and some of them won't. Yeah, there's a question back there.
It looks like one rule of thumb is that if it can achieve zero net churn number, it does. Is there a reason why that could be?
Yeah, there probably is, but I'll defer that to. Is there a good reason why that should be?
I don't have a,
I don't have a good reason. Yeah.
So no,
Good answer. Right.
splitting is small.
Yeah.
Splitting is small, like,
Yeah.
yeah.
It's yeah.
So these are symmetric representations of your group U4, I guess, right? To start with, manifold. I'm just cross-checking my understanding.
What do you mean by symmetric representation?
Meaning that just like the highest spin representations of any unitary group are symmetric representations. So I was going to ask, is this really a fancy version of Kunst? You're taking Coulomb interaction in this manifold, you're using it to split the degeneracies. And what Chris would be asking for would be a kind of Kunst rule.
I'm not sure. I mean, I would say that in fact what we're doing is we're where is it? Yeah, okay, it's sitting right there. It's up in the corner. We're actually breaking that symmetry.
Yes.
In some particular way. I mean, the highest spin representation of U4 plus U4. I don't even know what it would be.
I don't think it's what you wrote down at the beginning. The product of the. I'm not sure actually.
Yeah, I'm not sure. Yeah. Okay. Other. Yeah.
Make a comment about previous question about seeing these other ground states. So one of the ways you would see this near symmetry there, the near symmetry is you'd have modes that are soft for low symmetry reason. Modes that rotate your ground state into
Oh, I see. Yeah.
would be unusually low in energy. And people have not looked at those collective modes. So experimentally,
You'd say the finite energy, non-Goldstone modes.
non-Goldstone, but relatively low in some parametric sense. Other thing is that the energy splittings are small. So as you include other perturbations like phenols or things like that, there's a sub-manifold which is preferred and
Actually, I'm not sure that would be true actually, because maybe we should discuss it offline because I could start pontificating. Because in order to make because this is a global statement, that you would have, in order to make a low energy excitation, you have to be able to do something in a very small space, and you may not be able to make if there's a particular ground state and you want to go to a different ground state, you may not be able to do that locally. Right?
I'm just saying in terms of confidence level, this is like an anisotropy on an ferromagnet, let's say. And we're trying to get the sign of the anisotropy right.
Right.
But actually there are different levels of confidence in making that prediction. The antiferromagnet is the thing you're most confident about, and then which direction precisely it points in is a lower confidence statement.
Okay.
And if you see something that's completely not an antiferromagnet at all, then it's really telling you your starting point is off.
Okay. All right. Good. Yeah.
So where you write churn number 1 at the bottom, that's spontaneous time growth in the symmetry.
Absolutely.
Absolutely. Okay.
Anything else? Okay, good. Oh, so I want to focus in on the quantum anomalous Hall. So quantum anomalous Hall is interesting. It has been seen in experiment. I think Pablo showed this today. Did he show it yesterday also?
Yes.
Yeah. So I won't belabor anymore. But as you pointed out, it's actually quite unusual, and in order to get it, you actually have to align your graphene very carefully to the HBN. But if you do that, if you add that perturbation, then the quantum anomalous Hall does come out, which is interesting in itself. I'm making a small detour because there's some interesting features that you can get in Moiré systems that you don't get in quantum Hall systems. And so in quantum Hall, you might have some number of Landau levels, maybe a ground state, which is say 3 Landau levels still. And then if you think about what the low energy excitations are, well, the lowest energy excitation you can make here is to excite an electron up 1 Landau level. Now you went, in this case, you went from a Chern number +1 band to a Chern number +1 band. But over here, you can have a situation where you fill up some number of these Moiré bands, each with a Chern number, and you make an excitation from Chern number +1 to Chern number -1. And those actually make different types of excitons. The excitons in the quantum Hall state, they move straight. They see no net magnetic field. Whereas the excitons over here actually do curve around, and they actually make Landau levels, and they see an effective magnetic field. So you get some very different exciton physics in Moiré that you don't get in quantum Hall. So that's kind of interesting, and you can think about having, fractional quantum Hall effect of excitons or something like that. This was the project with Paul and a bunch of us. You can start thinking about if you have different possible symmetry breakings in different regions of your sample. Like, simple case, if it's a ferromagnet, you have spin up in one region and spin down in another region, then you can have a domain wall in between. And we know that the domain walls can be fairly complicated. They can lower their energy by twisting over slowly in some cases, and they can twist this way or they can twist that way. The difference between a nail wall and a block wall. And in this case, where you have some very generalized ferromagnets, you can get some very complicated domain wall structures, and there's a lot of interesting things to look at there as well. But I won't go into that in much more detail. All right. So let me give a couple of summaries of the good parts and things that the strong coupling picture doesn't get. So I think the really nice thing about the strong coupling picture is it gives you a way to understand why integer filling fraction gives you correlated insulators. That you have this flavor ferromagnetism, you fill up these bands individually, and that's really, really nice. But there's a couple of things that don't really come out right. Often in the experiment, the charge neutrality case is semi-metallic, but in this strong coupling picture, there's a fairly robust gap in the strong coupling picture. It's nu equals plus and minus 1. It's often metallic or just weak anomaly. I think I showed you that in the second slide or third slide. But again, it's very gapped in strong coupling. And nu equals 3 is always predicted to be quantum anomalous Hall in strong coupling, but in fact, you can get really good insulators that have 0 Chern number in the experiment. So we're going to go beyond strong coupling. And what I mean by beyond strong coupling is we're going to take the various perturbations to flat band seriously from the start. So non-zero chiral ratio, we're going to particle symmetry breaking terms, substrate potential, and the one that turns out to be really important is strain on the sample. Okay, let me say a little bit about strain. So with STM, you can measure the strain of the sample, and typically there's not, yes.
So you said that so experimentally people have measured the Chern number. So what's the
So all you measure is the Hall effect, and it's either quantized Hall or it is.
okay.
So in the experiment, there's the strain we're interested in is the heterostrain, the difference in strain between the 2 layers, which you can measure actually by looking very carefully at the details of the STM pattern, how the Moiré lattice is distorted, and the amount of strain you get is less than 1%. It's sometimes 0.1% or 0.2% or some number like that. But even with 0.2% of strain, the flat band actually changes its dispersion quite a bit. And this was pointed out, I think, first by Fuen's group, and it was pointed out by Ashwin's group that even this small amount of strain is enough to really degrade the KIDC gap at charge neutrality. That was one of the things that was problematic here. That charge neutrality is often semi-metallic in an experiment, even though strong coupling predicts a strong insulator. But if you use this strain more seriously as a starting point, the gap gets much smaller. So all we did was we put these things in,
Gap is smaller because the band is stuff.
it's okay, so it's a no, it's a bunch of things that have to go into the story.
So it's not obvious.
It's not, no, it's not an obvious statement, I think. So what we did was we basically just did self-consistent Hartree-Fock with as realistic parameters as we can come up with. And the additional thing that we added to be sure that we're getting as you know a good representation of the ground state as we could is we allowed for general translational symmetry breaking, so we can have you know charge density waves, incommensurate waves, and so forth. And so let me walk you through this plot. So each of these pictures is a different integer filling fraction. Along the horizontal axis is the strain in each picture from 0 strain to 0.3% strain. So the very small amount of strain that we're putting in, but it turns out to be important. And on the vertical axis is the coupling to the substrate, how well aligned you are to the substrate. And actually it's not people really don't know exactly how big that number is, but they have sort of a range for that number. And you'll see in every picture, okay, so a couple things to notice. So in the white hatched regions, there's actually no Hartree-Fock gap, although we can tell you what the Hartree-Fock ground state is, but it's not a gap system where the white hatched regions are here, here, and here. And you notice those line up with the cases which are, you know, semi-metallic in the experiment, which is nice. What's been circled here is IKS, which stands for the Incommensurate Kekule Spiral. And this seems to be fairly ubiquitous in the experiment whenever we have a little bit of strain. It certainly doesn't show up at charge neutrality, but it shows up here, here, here. And if you look at how much strain you need in order to push the system into the IKS state from the states that are sort of predicted in strong coupling, it's a tiny amount. In this case, over here, it's something like a few hundredths of a percent of strain is actually enough to do it.
Can just it seems right that most of these IKS are gapless, but 2 of them are where you say there's no gap.
So okay, so this is gapped, this is gapped, this is gapped, this is gapped. So this one is IKS, but it's gapless. Okay, this one doesn't show IKS, this one is IKS, but it's gapless. Okay, yeah. Yeah.
The gap comes from just a folding of the.
No, so the gap is just saying that you in Hartree-Fock theory, you fill the band, and then you have a gap, and then you have an empty band.
Yeah,
And it's gapless if the bands overlap.
Right, and so these bands that you're getting are basically coming from this, there's an extra periodicity in the IKS. Is that where it's coming from?
No, it isn't. So basically, you know, you take you take your bare bands and you add interaction. That's all you're doing. You add the interaction and perturbations, but because of that, your dispersion changes shape.
Okay.
You know, the energies go up and down, and it's only an issue of whether they go up and down enough that the bands start overlapping. If the dispersion of the band is big enough between, you know, compared to the spacing between bands, then you have,
But you're starting off with a band at the Fermi energy that's you know, there's no gap. This band, let's say crossing the Fermi. So this gap that you're talking about
so
is basically.
when you add interactions in Hartree-Fock, the bare dispersion gets normalized to a new dispersion, and that may be enough to flatten the band so that you can fill an entire band. Or it could be the enough to you can curve the band enough in order to make something that looked like it was going to be gapped into something that's gapless. So the interaction can change a lot. Yeah.
Can you translate the strain into electron volts?
You can, but I can't on the fly. So strains of that much, I think, are on the order of 100 Kelvin. I think that sounds about right.
So you mean the dispersion?
The bare dispersion, I think it's on the order of about 100 Kelvin. Yeah. Maximum. I think I'm just pulling that out from sort of roughly where the number is, but I could have that wrong by then. So okay. So a couple other things that you see here, you'll see at low strain, nucleus +2 and nucleus 0 and -2 do show in the Hartree-Fock show the KIBC state, which is what was previously predicted. Yeah.
You mentioned that you add possible symmetry breaking from
Yes.
observations here, but just kind of by eye, it doesn't look.
They look fairly particle symmetric. Those are weak terms. I mean, if you look at where this hits 0, this is sort of at half of 0.1%, and this one looks like it's about a tenth of 0.1%.
So
So
how
slightly bigger.
So how important are those?
They can be fairly. They can. I mean, it's not hugely different, but you know, it can be enough to change the physics, and so in the experiment, they're definitely not the same. Yeah. It's not a bad approximation to say it's particle symmetric, but it's not exactly true. Okay. All right. So what is this IKS state? Well, it has a particular version of time reversal symmetry. It breaks U1 valley symmetry, meaning it has superposition between the two valleys, which means it's going to have this k minus k prime wave vector or tripling of the itself. It breaks translational symmetry, but it preserves a modified translational symmetry where you translate by a Moiré latticite and you rotate the valleys at the same time. Okay, that's the order of the system. You have a symmetry under translation and rotation between the valleys. That's a useful symmetry to use because then you can use Bloch's theorem and so forth. So let me try to give you some idea of what the physics of the state is. So most of the time when you think about intervalley coherent states, what you do is you look at the k valley and the k prime valley, and you pick a point in the k valley and you superimpose it with the same point in the k prime valley to make a superposition. Then you put that in a spinor state and you point in some direction. Here, what I'm saying is that you pick a point in the k valley and then a point in the k prime valley, which is displaced by a wave vector q. That's the wave vector of this incommensurate wave vector. The energy is, the energy as a function of this q is very soft. You don't have, if you choose that q a little bit wrong, it's it only hurts your energy a little bit. If you choose it completely wrong, it hurts your energy a lot. Oops.
Yeah, that's a bit too.
Yeah. If you choose that energy, if you choose that Q really wrong, the energy is hurt by a lot. Not a lot, but enough. So it's a fairly soft number, and it depends on details. If you change some of the details of your model, this Q will sort of flop around a little bit. There's nothing particularly special about that value of Q. So because it couples the valley, you have this tripling of the cell. There's a Kekule density distortion, and then the Kekule phase rotates with this wave vector Q between the Moiré sites. So this is the picture I showed you in the first slide. So let me try to now give you an idea of why it is that you would want to do this. Why is it the physical system wants to do this? So it's a little bit of a complicated slide, but let me try to walk you through it. So this is as the color here is the energy within the Bronze zone, and here I'm plotting the energy of a band in the Bronze zone under the conditions that I'm not going to allow it to form intervalley coherence. So I'm going to stop the intervalley coherence. I'm going to plot the energy in the Bronze zone, which has now been renormalized by all sorts of interactions and other effects. Now, so this band has some shape. It has a high energy lobe here and a low energy lobe here, and this time reversal partner over here will have exactly the opposite: high energy lobe here, low energy lobe over here. And if you think, well, what do I want to do to make the energy low? You would just say, okay, this looks like a metal. If I want to fill this up with a total filling fraction of 1, I'll just fill the low energy states here, low energy states here, leave these states in the middle empty, and that would be the right thing to do. But if you allow intervalley coherence, you can pick up some energy. This is what drives the interlayer coherence states. The idea of this, of making intervalley coherence at a finite wave vector is the following. If you shift this bronze zone with respect to this by a wave vector Q, you can line up the high energy lobe of this bronze zone with the low energy lobe of this bronze zone, and the high energy lobe of this bronze zone, low energy lobe of this bronze zone, the high energy lobe of this bronze zone. So then what you have, look at this map here. Everywhere in the bronze zone, you make sort of an equal superposition of the two bands. So you're making an intervalley coherence state between the two bands, and you're sort of putting that pseudospin vector in plane. But when you get to a point in the bronze zone where one of the bands has a particularly high energy and the other one has a particularly low energy, you can then pop the spin out of the plane, take advantage of the low energy and not pay the high energy, and then go back into the plane in order to pick up the intervalley coherence energy. And then when you get to the opposite lobe, you push the spin the opposite direction to pick up the low energy part of the other band. So what you're trying to do is you're trying to get this low energy here and this low energy here, and not pay these energies here, and also get the intervalley coherence energy. Okay, that's the physics that drives this. Okay, and in order to get this, you have to have dispersion of the bands. If the bands were completely flat, there would be no particular reason to try to realign the bands, because this is entirely coming from the fact that you don't want to pay the energy in some parts of the zone. That's what's going on here. Okay, so a couple of things that connects IKS to experiment. So the strain degrades the gap, and you end up getting semi-metal at charge neutrality. Nu equals plus or minus 1 comes out correctly. It's sort of a near insulator. It's gapped at nu equals plus or minus 2. That's something that's still polarized. Gapped it at nu equals plus 3. It has strain number 0. And it emerges at strain ratios which are within the experimental limit. But the big thing is that you can observe it in STM. So this is a beautiful experiment by Ali Yazdani. And how much time do I have?
40 minutes.
40 minutes left? Oh, I'm going to finish early, so we'll all go home and have a drink or something. Okay. So the way this experiment goes is you basically you do STM, and the assumption is the STM is basically telling you the local density. This is a picture of the AA region of one of these Moiré systems. And you can see, you can look closely, you can see the individual graphene hexagons lying under that. So you take one of these AA regions, a big chunk of these, and you Fourier transform the picture. Fourier transform the picture, what you mainly see at many filling fractions is the graphene drag peaks. You see the periodicity of the underlying graphene lattice. That's not surprising. But when you hit a filling fraction -2, which is where we expect incommensurate Kekule spiral, you also see these additional Bragg peaks. These additional Bragg peaks are the Kekule distortion. It's a tripling of the unit cell, and you can figure out what the Bragg, the appropriate size of the Bragg wave vector is, which is slightly smaller than the underlying graphene. So this is the triple unit cell graphene Bragg peaks, and this is then just this is G, this is 2G, this is 2G, it's just the multiples of those. Okay. Now, the fact that you see a Kekule distortion tells you immediately that, well, one, you have intervalley coherence because you have this wave vector which connects together those in K and K prime, which is exactly what you need for to see this Kekule additional periodicity. But it's not KIVC, because KIVC is not supposed to have a density modulation. Because of its time reversal symmetry, it only has currents moving in this triple unit cell. So that eliminates KIVC from contention. Now they go further in this experiment. They look at not only the amplitude of these additional Bragg peaks, but they look at the Fourier transform phases of those Bragg peaks. Now, it turns out because you're measuring a real quantity, there's 6 Bragg peaks, but there's only 3 independent complex numbers to measure. And what they do is they basically plot in some linear combination, those 3 independent complex numbers that they measure in the Bragg peaks, and they plot those 3 complex numbers of the Kekule Bragg peaks as a function of position. Okay, so when you do that, you get these pictures. So what this is telling you is that the periodic pattern is changing as you move through the lattice. It always has the peaks always occur at the same place. The peaks always occur at the same place at those Kekule Bragg peaks, but the phases and amplitudes change as a function of position. Actually, here's a picture of 2 of the Bragg peaks looking like they've vanished here. Here they've vanished completely, and then here they're back again at different points in the sample. So they plot the 3 independent phases and amplitudes in this sort of color plot here as a function of position in the sample, and you see that they okay, so this is the Moiré unit cell going from AA to AA to AA to AA, and the phase of this distortion is changing from one color to another color to another color, and then back to roughly the same color. So this particular wave vector is roughly 1/3 of the bronze zone. So you get back up roughly exactly where you started after 3. So here, and then the 3rd time it's not exactly lined up with where it was before, but it's pretty close. This down here is a DMRG simulation of the IKS state by Mike Zalatel and Tomo Sujiro, which matches fairly well with the experiment, although the actual direction of the wave vector for the Kekule spiral doesn't match exactly. It's actually matches fairly well, and being that we know that the energy is a fairly soft function of the actual value of Q, that seems to be pretty good. And any questions on that so far? Yes.
Yeah, the question about, so the strain is, I guess, somewhat random in the system.
The strain is probably fairly uniform in the system. If you go from one system to another, it's random. Yeah, I mean, probably does change a little bit from place to place, but over some fairly large region, it's pretty constant.
So you just said you did a DMRG calculation.
Yeah.
So this is for fermionic model, speedless, long-range Coulomb interaction, right?
No, I think it's spinful.
Okay.
And it has Coulomb interaction, it has substrate potential, it has all the perturbations put in that they could think of.
Okay.
Yeah. Yeah. Mike is a master of DMRG.
Okay.
Yeah. Now, so this is what they see are Ali and Kevin and the collaborators say they see this in typical samples. This is seen all over the place, except for a few samples with ultra low strain, they see something different. Okay, and that's okay. But oops, okay, let me skip this. We can look at non-integer fillings as well. Maybe let me skip that for now. Okay, let's look at some of the non-integer fillings. So this is the filling fraction 2. This is 2.19. You can see that something's changing as you go from place to place to place. It's not as obvious that this is exactly the same as this. So I'm not going to stick my neck out and say this is definitely IKS, but it looks IKS-ish, if that's a word. And even in the superconducting region, at filling fraction minus 2.41, they see something that kind of looks IKS-ish, but it's not necessarily IKS. Okay. Right. What about the highly unstrained samples? Well, okay, we had this at nu equals -2. We had this picture that you should see IKS, and then at low strain you should see KIPC. That doesn't agree with the experiment either, because in the highly unstrained samples, they do see Kekule patterns. The Kekule patterns don't change as you go from place to place to place to place. They're completely more periodic. So there's no incommensurate wave vector, but it also doesn't match KIVC because KIVC shouldn't have a Kekule pattern at all. So we were really scratching our head over this actually, and we couldn't figure out what was going on. And then this guy who was here a few moments ago but left, said, well, phonons, of course, and he was right. And the point here is that phonons will stabilize a density modulation. Phonons like density modulations. So if you turn on enough electron phonon coupling, you will stabilize a different state of matter, which is neither IKF. So this axis here is the strain, and this axis here is now electron phonon coupling. So IKS at high strain, KIVC at low enough strain. When you get down to very low strain, it's KIVC. But if you turn off the electron phonon coupling, you get into a phase of matter where we can't identify it, and there's a remaining symmetry, and we don't know how that symmetry breaks. But both of these would be in agreement with the reasonable agreement with the experiment. So that sort of made us a little happier that it wasn't completely out of the question, that everything falls, everything still kind of works. Trilayer. So just a few weeks after Ali Insani's experiment, the Caltech group with Stefan Najperg announced that they had seen IKS order in trilayer graphene. So this is the case that we probably spoke about this morning, where the first and third layers are aligned with each other, and the middle layer is rotated to 1.54 degrees instead of 1.1 degrees. And in this case, you get a flat band, just like you have in the bilayer case. So basically, the spectrum is, before you put in the interactions, is the spectrum exactly of twisted bilayer graphene plus one Dirac cone left over. So you have a flat band in the middle and the Dirac cone as well. Now, how different is this from the bilayer? Well, to be fully honest, we haven't absolutely completed our calculation of this. We want to do we're in the process of doing a full Hartree-Fock, but it's actually a little bit more complicated because you actually can transfer some of the density from this from these flat bands into the Dirac cone. Some of the density goes back and forth, but roughly there's a lot of situations under which Hartree-Fock also predicts IKS state. But in the experiment, they see it fairly clearly that there is an IKS state. And the way they do it is actually using a slightly different technique. So again, you basically, you take a STM of a very large region, and you can identify their graphene peaks, then additional Kekule peaks. Okay, so you have the graphene hexagon you see, then you see this smaller Kekule hexagon. But what they do that's different is, first of all, they have a very big sample with no defects in it. And they scan the very big sample. And that enables them to get really high precision pictures where you can see that each of these peaks is broken up into lots and lots of little sub-peaks. Those sub-peaks are the Moiré periodicity, okay? And so these G is for let's see, G is for graphene peak, and K is for Kekule peak. So they find the graphene peaks here, point G, and they find the Kekule peaks here. But the Kekule peaks aren't exactly at the position they're supposed to be at. They're supposed to be exactly, a factor of square root of 3 smaller, and you can triangulate in and find out where they're supposed to be. They're actually displaced a little bit. And that little displacement is the Q vector that they measure, and they measure this Q vector. Okay, so they measured it. Okay, well, the actual thing that they plot is the IKS plus a Moiré unit cell vector here, but it changes as a function of the filling fraction, and it's sort of a continuous function of the filling fraction going down to filling fraction -2. So it's a fairly convincing evidence of this additional wave vector. Summarize the incommensurate Kekule spiral. It's there in typical samples. Almost all the samples that they look at have these incommensurate Kekule spirals at various integer fillings. There are things that look similar to it at non-integer fillings, but maybe not exactly what we predict. It explains a lot. How much more it will explain, that will remain to be seen. And I guess I'll stop there and answer any further questions.
I have a question about phonons, given that
Yes.
you understand them better in the slow strain samples. What can you say about their role, yes or no, for superconductivity?
Yeah, it's a good question. So there's a lot of people who have said, you know, there's no matter what, there's a theorem. No matter what you see superconductivity in, someone's going to say it's phonons. Okay, and sure enough, that's true. Some people immediately said, look, it's phonons. There is fairly strong electron phonon coupling in the system at the Kekule wave vector. I don't want to give away a paper we're writing right now, but we're studying it. We're studying this in some amount of detail at this point, but I'm not optimistic in having an ironclad argument that it's actually phonons, not without some additional physics put in. So that sort of gives away that punchline. Yeah.
Just related to this, given like if you think of superconductivity is something that is coming from doping IKS sort of, is there some very generic comment that can be made about superconductivity in terms of what?
Yeah, so this is exactly what we thought. We thought the parent state is IKS or IKS-ish. It's not actually obvious that that's true. If I look up here to this data, I mean, this, if you take some random filling, 2.38, 2.56, which is not integer, it's not exactly, it doesn't look like it's exactly IKS, but it looks IKS-ish. We can do a Hartree-Fock and find something that looks like it's low energy, it looks like it's IKS-ish. And you can imagine using that as the parent state for superconductivity. That's exactly what we did. There's no particular reason why you would think that that is incredibly favorable for superconductivity as compared to other physics, some other starting point. So I don't have any good argument for that would be it. I mean, it could be that it's something that something in the IKS is really crucial to superconductivity, but you need a mechanism which is more complicated than something simple like phonons. I mean, one of the challenges, as Pablo said, is that the experiment seems to indicate that it's not just regular S wave. And phonons, the first thing they'll give you is regular S wave. Then you can sort of work a little bit to try to get them to give you something that's not regular S wave, but now you're already starting to explain, you need, either story is getting more complicated. So
Chris.
Thank you. Yeah, so great talk.
thank you.
Pablo pointed out to us this morning something that I hadn't previously been aware of, that the actual structural position of the atoms in twisted bilayer graphene is quasi-crystal,
Yes,
even though the AA structure is periodic.
by some definitions, yes.
Does that give us some, is that connected to the softness of this Q, or are they unrelated?
I think it's unrelated, actually. I think the softness of the Q is entirely a numerical statement. If you allowed me to tweak the interactions in any way I wanted to, I could make the Q less soft. But it's just none of these things are particularly sharp in the Brown zone. You need sort of some sort of dispersion which has deeper dips in the Brown zone, which will care exactly how you line things up. And these are, you see, they sort of have these bowls in regions of the Brown zone, and you can, as long as they're sort of pretty close to each other, the energy is good. But if they were real sort of sharp dips, you'd really want to align them perfectly.
Yes, maybe it's such a good one, but does the direction of the strain play?
It does play a role. Yep. If you change the direction of the strain, the Q vector will move. It tends to sort of hang independent of direction. It tends to sort of hang around, sort of half the Moiré burns, sort of around half or a third or 2/3. It doesn't tend to go to the corners or the middle. And it does depend in some way, but in some complicated way. So you choose some direction of strain, and
The general features are robust.
the general features are fairly robust, yeah, but it's it does depend. It depends on lots of details.
Ashwin.
So in the experimental paper, the stunning paper, they was sort of suggesting the finite doping is more like your phonon-induced state, right? Well, it sounds like you feel maybe it's more like IKS.
Well, the question is if you compare the pictures, so for example, in this picture here, it really looks periodic. It really looks more like periodic. And if you look back to the sort of that's a low strain sample. And if you look back at this one here, it definitely seems to be rotating slowly.
But, I think with strain, there's no symmetry that protects you to be at the zero momentum. So when you have C3, then it's really protected. So even if it is not, like, let's say it was TIBC,
yeah,
the wave vector would drift off. Because the actual state is quite different from IKS, where it's really this nesting and all that.
Yeah.
If you just look at the wave vector, there's nothing to log it in.
Yeah.
Don't have C3.
Okay, yeah. Let me think.
Yeah, so if I took your TIVC and
Yeah, so
C3, it could sort of wander off.
Yeah, so we found a fairly sharp transition from
Yes.
finite to zero. And it may be that it's very soft at zero to very close to zero or something. So it may be that what you're seeing here is something that wants it could be that what you're seeing here is something that wants to be zero, but is slowly modulating a little bit. But it doesn't look that slow either. I mean, from here to here, it's like 4 Moiré unit cells, and it's gone from green to green. So it's, I mean, over here, we 3 unit cells. So it could be finite wave vector. It doesn't. I agree. It doesn't look exactly like the KIVC that you see at nucleus +2. But
the IKS.
Sorry, the IKS that you see at nucleus +2. But it does look like it's modulated at some finite Q. At least to me it does. But maybe it is close to zero and just wandering a little bit. It's hard. It's a little hard to tell. I think they were a little bit sketchy about exactly what they think is going on there, and I'm not going to put it. When you compare Mike's simulation against the experiment and knew it was 2, you can say, yeah, that's it. There's no question that's what's going on. But in this case, yeah, it could be something related or it could be something different. It's not. It doesn't look like a slam dunk, so I'm not really sure. Yeah.
Okay, quick related question is, you put a 0. Did you did the same for calculation, right?
I think we did. But I don't remember what the answer is there.
I think at least experiments, they see a gap and they didn't report.
Yeah, we definitely did. We definitely did. I just don't remember exactly what the result is. I think the I don't remember. I should just look it up in the paper. I don't remember.
We'll ask a question. These is one of the little bit of SSH type physics in one dimension, and you're really forming these contractions of the bonds from very high frequency modes of the
of the lattice electron system. So given that they're so high frequency, wouldn't they occur every time you hop an electron in and out of one of the Moiré Vanier states? In other words, the valence fluctuations in and out of the local moment states, wouldn't they occur as a breathing mode?
So do you mean once you're coupled to phonons or not worrying about phonons?
No, I'm worrying about, of course, I'm worrying about phonons. So phonons seem to be high frequency compared to the flat bands, and therefore aren't we in an extreme polaronic limit where valence fluctuations of the Moiré states will always occur in tandem with a breathing mode of phonons?
Yeah. So so the scheme that what we integrate out the phonons and then we just solve the problem as a and you can start looking at things like response, where you have to bring the phonons back, then affect the phonon back in. We didn't do
In
that.
other words, if I think of this in the Sombrero picture, each time I change the occupancy of these localized Vanier states, presumably I will add phonons as well,
Right.
create a
That's
coherent
right.
state
Right.
of phonons that come in.
Right.
That would then renormalize one of the parameters very
It's
heavily.
virtual.
But since they're fast,
Yeah.
this is a problem that was thought about in heavy electrons decades ago and doesn't occur there because the electrons are too fast for the phonons to respond. But here it looks like it's the other way around, that as the electrons hop in and out or hybridize in the Sombrero picture with the localized Vanier states, the phonons will have to respond.
So
I was wondering whether you had any feeling for that.
I don't. I mean, one of the things that we spend some time thinking about is whether we should be thinking in terms of polaronic hopping. And the only thing that makes me think that might not be going on is because if it was a strong polaronic hopping effect, I would expect the bandwidth to get really flat, because you have to move the phonons with you, and I don't think the band. I mean, if you had that level of flatness, then you would go back to the strong coupling picture pretty effectively, I think. I could be wrong about that, but I think that's my intuition. We're not seeing the the phonon physics that really prevents.
Well, it depends, it's e to the minus the number of bosons typically that you get,
right,
so it's a question of how many
how
bosons you bump into that exponential.
Yeah.
Okay.
Yeah.
All right,
Yeah,
thank you. Yes, over there.
All right. So what does the experiment see at mu equals ±1?
So the scanning experiment.
Yeah.
So I don't believe that there's data at ±1. That they like, it didn't show us, as far as I know.
Sorry, were you?
Yeah, no, that's it. It's also I mean it's not insulating. So maybe that's why they weren't interested. But and there could be other. I mean, experimentalists are very cagey when you ask why haven't you done X, Y, or Z. They sometimes don't tell you exactly why they chose to do one and not the other.
Second follow-up question. How exactly do you incorporate strain in your calculation?
Yeah, so we basically it acts like a gauge field. We followed basically the.
Is this at the monolayer level or do you?
Well, you're the strain that's interesting is the hetero strain, so you have to keep that, but it enters it as a gauge field. It's we basically followed the Liang Fu's approach to it.
Last question, yeah.
Okay, so I was wondering if this analysis with all of these extra perturbations and maybe Kekule spiral that is present in the experiment helps in clarifying why the hexagonal boron nitride is so important for the correct alignment for seeing this quantum physics.
Yeah, no, well, okay. I mean, so I think yes. So you can yeah. So here. So this is exactly right. So if you're okay, so nucleus +3 is where you see the quantum Hall physics. If you have a little bit of strain, you see IKS, which is not a quantized Hall state. But if you crank up the alignment with the boron nitride substrate potential, you get into a quantum anomalous Hall state. So that's exactly right.
Okay, good.
And thinking in an origin to the future, so you are thinking about how the present ITS states are devised in transition
The what was section?
kind of factoration, spin factoration.
Oh, yeah.
Yeah.
So you're saying in terms of, if you're thinking about an interaction, so another theorem, anytime you see a superconductor, someone will say phonons, but someone will also say not phonons, it's interaction mediated. And if you're looking for an interaction mediated mechanism, and I'm starting to be fairly sympathetic that interactions have to be somehow important, then you're going to have to look at fluctuations of something as being the relevant boson. I mean, Ashvin and his friends had a really neat picture of in terms of skyrmion superconductivity, and then you find a type of glue which is very non-traditional. Whether that picture will hold up to scrutiny, I don't know, but if you were looking for other sort of interaction mediated schemes, you would have to construct a boson from some of the fluctuations within this manifold, and then use that as the glue. That's something that's at least typically interaction mediated, gives you an exotic order parameter, and that might be useful for the matching up with the experiment that seems to see not S wave or not singlet.
Okay, that seems like a really good point to stop. Let's thank you. Before you all go, I just wanted to say that this event does